Welcome to Maths with EJD. We're still talking about real analysis, and this video focuses on sequences and series of functions, comparing pointwise versus uniform functions. In previous videos, we had considered sequences of functions in real analysis and also series of functions in real analysis separately, but here we are zeroing in on comparing pointwise versus uniform functions, right? Okay, so let's go into that. The core concepts and definitions, first of all. So when we talk about sequences of functions, right, we have pointwise convergence on a set E. So we say a sequence Fn converges to F pointwise if for every x that belongs to the set E and every epsilon greater than 0, there exists n, which is a function of x and epsilon, such that for all small n greater than or equal to big N, we have the absolute value of fn of x minus f of x to be less than epsilon. So, I mean, it's talking about the general concept of convergence, except that here we are dealing with a sequence Fn converging to a particular function f. Okay, then we have uniform convergence on E. So it's pointwise and then uniform. So for uniform convergence on E now, we have the fact that a sequence Fn approaches F uniformly if for every epsilon greater than 0, there exists n equals n of epsilon, such that for all n greater than or equal to n and all x belonging to the set E, we have the same expression. Absolute value of fn of x minus f of x is less than epsilon. Now, single n works simultaneously for all x, actually. Okay. Now, we talk about series of functions. We say that a series of functions, summation from n equals 1 to infinity of fn, converges pointwise on E. Okay. If the sequence of partial sums. So when we talk about partial sums, we're talking about things like maybe the first partial sum is like f1, and then the second partial sum will be f1 plus f2. The third partial sum is f1 plus f2 plus f3, and so on and so forth. So, so if you take a particular n, you know, so if it converges pointwise to a function s, then we say it converges pointwise on E. So in that case, it converges uniformly if Sn approaches S uniformly on E. So that's talking about pointwise and uniform convergence. Then we have the Weierstrass M-test, and here we have the informal statement. Okay. If the absolute value of fn of x, the absolute value of the sequence fn of x is always less than or equal to m sub n on E for all n, and summation of m sub n converges, then we say that the summation f of n, summation fn converges uniformly and absolutely on E. Okay. And then we can talk about the idea of we can talk about the idea of termwise limit, integral derivative, and their typical criteria right here. Okay, so here, if if the sequence fn approaches f uniformly on E, and each fn is continuous, then we say f is continuous on E. On the other hand, if fn approaches f uniformly on the closed interval AB, a comma b, and each sequence fn is Riemann integrable, then we say that the integral from a to b of fn dx approaches the integral of f dx from a to b. So if now fn are differentiable, if the sequence fn are differentiable on the closed interval a comma b, and fn of x naught converges at some x naught belonging to the closed interval ab, and fn prime approaches g uniformly on the closed interval a comma b, then fn approaches f uniformly for some differentiable f with f prime equals g, like that. And then that takes us to the idea of power series. I have a playlist on power series where we dealt thoroughly with the idea of power series, like this. So here, okay, I think I can display everything at once like this. So we're talking about power series basics. Okay. All right. So a power series centered at A. So there's a center, right? If A is zero, then we can just have x raised power n. So a power series centered at A, so that is summation from n equals 0 to infinity of Cn into x minus A raised power n. So if the center is zero, then we just have Cn x raised power n, basically, right? And then here we talk about the radius of convergence R, going by Cauchy-Hadamard. So 1 over R is a limb sup as n approaches infinity for the absolute value of Cn raised by 1 over n. So that is how we get the radius of convergence. So if you check the playlist on power series, so I explained how to derive the radius of convergence for each kind of series. Equivalently, when limits exist non-zero, we have the ratio test such that R now is equal to the limit as n approaches infinity for the absolute value of Cn over Cn plus 1. And then we also have the convergence behavior. So, so we say the power series converges absolutely for absolute value of x minus a less than r. So x minus the center, absolute value. If that is less than r, we say we have absolute convergence. Then of course we have divergence if the sign is changed. That is the absolute value of x minus a is greater than the radius of convergence. Then we can have a boundary if the absolute value of x minus a is equal to the radius of convergence, and that must be checked term by term. So that so in that case, we really want to be sure that it doesn't fail at any point. Okay. So inside the absolute value of x minus a less than r, termwise differentiation and integration are valid, and convergence is uniform on every closed subinterval, say a minus r to a plus r, with r being less than the radius of convergence itself. So that's talking about some basics about power series, since we're talking about sequences and series in general. Okay, let's look at some proofs here. Hmm. So some proofs you should know, clean and exam ready proofs, that is. So for Weierstrass M-test, the full proof now. So we say that if the absolute value of fn of x is less than or equal to m sub n on a set E, and then the summation of all mn actually converges, then the summation of the series converges uniformly and absolutely on the set E. That's the theorem we need to prove. And the easy way to go is we fix an epsilon greater than 0. That's some positive value, very small, but greater than 0. Since the summation of all m and n converges, then we can choose a particular n with summation from n equals p to q of m sub n less than epsilon for all q greater than or equal to p greater than or equal to n. If you reverse it, that's like n less than or equal to p less than or equal to q. That means that p lies between n and q, right? So we also say for any x that you take from the set E and q greater than or equal to p greater than or equal to n, we have the absolute value of summation from n equals p to q of fn of x is less than or equal to the summation of the absolute value of fn of x from n equals p to q, and that is less than or equal to the summation from n equals p to q of mn, and that is less than epsilon. So in that, with us, we can say that the sequence Sn of x now is a Cauchy sequence uniformly in x. Of course, I'm sure this is the sequence of partial sums, right? Is a Cauchy sequence uniformly in x. Hence, we say summation Fn converges uniformly. So absolute convergence follows similarly since the summation of the absolute value of Fn of x is less than or equal to summation of Mn, like that. Okay, and that takes us to the idea of uniform limit of continuous functions. Uniform limit of continuous functions. Uniform limit of continuous functions is continuous. So the uniform limit of for continuous functions is actually continuous. So if you talk about continuous functions and you take their uniform limit, then that limit is also going to be continuous. That's what this is basically telling us. Therefore, if the sequence Fn are continuous on the set E and Fn approaches F uniformly, F is the limit. If a function that it's approaching uniformly, then we say F is continuous on the set E itself, right? So the limit of this continuous function is actually continuous itself. That's the deal there. So the proof, so fix x naught, which is an element of the set E, and then fix epsilon greater than 0. And then you want to pick a particular n with absolute value f big N of x minus fx is less than epsilon divided by 3 for all x that is a set, that is an element of E, right? So by continuity of Fn at x naught, we can choose delta greater than 0 so that, remember this whole idea of continuity that, for something to be continuous, we have a particular, for every epsilon greater than or equal to 0, we have this expression that the absolute value of x minus x naught, less than delta implies that Fn of x minus Fn of x naught is actually less than that epsilon over 3 that we talked about here. In that case, we can now say then for the absolute value of x minus x naught less than delta, then absolute value of f of x minus f of x naught is less than or equal to absolute value of f of x minus f of x plus fn of x minus fn minus x naught. Basically, what we are bringing here is the whole idea that, of course, we have x and x naught. So if you take their functions like that, so that is going to be less than when you have this x minus fn plus when you now have fn minus fn minus fn x naught, right? Like that plus fn x naught minus f of x naught, fn of x naught minus f of x naught, and that is less than epsilon. So with this, we can say, so f is continuous at x naught, like that. So I think the deal here is that, this is less than epsilon over 3. So if each of them, this is less than epsilon over 3, this is less than epsilon over 3, this is less than epsilon over 3. So if you multiply epsilon over 3 by 3, you get this epsilon right here. And that is what we have here to establish that continuity. Then we talk about differentiation under the limit sign for, and then talking about uniform derivative. So here, the theorem is, suppose Fn, all the sequence Fn are differentiable on the closed interval a comma b. There exists x naught belonging to a comma b with Fn of x naught approaching limit L and Fn prime, the derivative of the sequence Fn is approaching G, uniformly on the closed interval AB. Then we say that Fn actually approaches F uniformly on AB for some differentiable F with F prime equals G, right? So the idea of proof is something like this. So you define an F of X as L plus integral from X naught to X of G of T dt, right? So by the fundamental theorem of calculus, I think we saw this in an earlier video. So we say F is differentiable and F prime of G, F prime is equal to G. So for each n now, you can say that Fn of x minus Fn of x naught is equal to integral from x naught to x of Fn prime of t dt, right? So having done that, of course, if you try to integrate this function, so if you integrate this function, the prime will be gone, and then you evaluate at x, and then minus Fn of x naught. So that this holds from the idea of integration. So, and then we see that uniform convergence Fn prime to G plus Fn of x naught approaching L gives uniform convergence of Fn itself to F via uniform control of the integral. And then we go for integration under the limit, talking about uniform convergence or domination. Okay. So first of all, we have theorem, the Riemann version. If Fn approaches F, if it converges to F uniformly on the closed interval AB, and each Fn is Riemann integrable, then we can say that the limit as n approaches infinity of integral from a to b of Fn is simply the same thing as integral from a to b of f. So that establishes that idea of convergence. And the proof sketch is something like uniform convergence allows you to make this, that the supremum over x of the absolute value of Fn minus f is actually less than epsilon over b minus a. Hence, integral from absolute value of integral from a to b of Fn minus f is less than or equal to b minus a multiplied by the supremum of Fn minus f less than epsilon, like this. Okay. So what's basically happening here is that if you multiply both sides by b minus a, you have b minus a multiply by this, and that's less than epsilon. And then and then the integral from the absolute value of integral from a to b of fn minus f is now less than that expression like that. So in the Lebesgue setting, one often uses the dominated convergence theorem or the monotone convergence theorem instead of uniform convergence. In a previous video, we had looked at MCT, that's a monotone convergence theorem, where we established the idea that a monotone function or a monotone sequence, if you like, is actually a sequence that is either increasing or decreasing, right? Like that. So let's look at some techniques and quick checks we need when we talk about when we talk about sequences and series, with focus on pointwise and continuous functions. Pointwise, right? So let's talk about techniques and quick checks here. Techniques and quick checks. So first of all, okay, yeah. So uniform versus pointwise via the soup norm. So Fn converges to F uniformly if and only if, if and only if means you prove it forward and you prove it backwards. If and only if uh the norm of Fn minus F to infinity, infinity actually approaches zero, right? And then you have Cauchy in soup norm. Uniform convergence is equivalent to the sequence Fn being Cauchy in C of E, with norm going towards infinity. Then you have the Dini's theorem, a preview of that. On a compact set, if Fn approaches Fn pointwise and all Fn are continuous, then convergence is uniform. Then you have uniform convergence the fact that uniform convergence preserves continuity, integrals, and differentiation with uniform convergence of derivatives and one anchor point. Then you have M-test pattern. So try to bound the absolute value of Fn of x by less than or equal to Mn with summation Mn geometric or P series. Then we have power series rules. So you can use root or ratio test for radius of convergence R. Then uniform convergence on the closed interval a minus r, a plus, comma a plus r with r less than r. Then you have the termwise differentiation or integration, which is valid for the absolute value of x minus a less than the radius of convergence. And then you check each boundary point separately. I think we established that earlier on in this place. So if you have, so of course, boundary points occurs where the absolute value of x minus a is equal to the radius of convergence. So we have some worked examples to consider, talking about pointwise versus uniform. So look at example 1. You have x raised power n on 0, 1. So you want to confirm if it converges pointwisely or uniformly, right? So let's start with, so define first of all Fn of x equals x raised power n on the closed interval 0 to 1. So when we do pointwise now, what we have doing here is we take x, which belongs to the semi-closed, semi-open, half closed, half open interval 0 to 1. This simply means that we have 0, but then 1 is excluded somewhat. So in this case now, for x in this semi-closed, semi-open interval, and then imagine the fact that xn approaches 0, right? So we see that at x equals 1, we have x raised power n, which is equal to x raised power. So at x equals 1, right? When x is equal to 1, we have 1 raised power n, and that's simply 1. So in that case now, you see that we can now say, so f of x will actually be 0. It will be 0 between, when x lies between 0 and 1. Zero with 0 included now. So starting from 0 to somewhere before 1, so the function is defined as 0. But at x equals 1 itself, the function is 1. So it becomes a step function like that. So we see that the function x raised power n converges pointwisely. It converges pointwisely. Now the question is, does it converge uniformly? So the question is no. If convergence were uniform, then the absolute value of Fn minus F going towards infinity should be 0. But for Xn, right? So if you take for Xn, we have Xn equals 1 minus 1 over n. So if we have Xn to be 1 minus 1 over n like that, so Fn Xn will be 1 minus 1 over n raised power n, and that approaches e raised power minus 1. If it was plus, it would have been e raised power 1 or something like that. Okay. So with f of xn equals 0 now. So so we have this approaching e raised power minus 1. So while f of xn itself is equal to 0. So thus we see that the supremum of x belonging to 0, comma 1 of the absolute value of fn of x minus f of x does not converge towards 0, because that's the condition. So in this case now we can say that the function x raised power n on the closed interval 0 to 0, comma 1 is pointwise. It converges pointwisely, but it is not uniform, right? It converges pointwisely, but not uniformly, like that. Okay, so we have another one. You have fn of x equals x over, okay, I guess we can still expand this. Nice. Okay, so example 2, fn of x is actually x over 1 plus n x squared on the real number line. Okay, so for pointwise limits, we say for fixed x now, denominator grows as n. So fn of x approaches 0. So what we are saying here is that for any fixed value of x, so as n is growing, it means that this whole denominator will become larger and larger. And as this denominator becomes larger and larger, and because x is fixed, right, the larger n becomes, the likelier this expression approaches 0, right? So as n becomes very large, as n approaches infinity, that is, fn of x will approach 0 because it's at the denominator. And once you have a large number at the denominator, you are going to be having values closer and closer to 0 as the n value increases. So that's for pointwise limits. Then for uniform convergence, now you want to compute the supremum norm, which is absolute value of fn of x equals absolute value of x all over 1 plus nx squared. So if you maximize over x greater than or equal to 0, you have a critical point, right, at x equals 1 over square root of n. So what's basically happening here is this, let me see. So it's more like we're doing some kind of equating to 0 like that. And, in that, so it's more like you have 1 over 2nx. Yes. So it's like we have 1 over 2nx equals 0. 1 over 2nx. Oh, okay, like that doesn't work. 1 over 2nx. Okay. So from there, this x now, I mean, this x, or it's more like we equate this part to 0, right? So 1 plus nx squared equals 0. Okay, that's going to be negative right there. Okay. So ensure we have a critical point at x equals 1 over root n, which gives that the absolute value of f sub n, to infinity is 1 over 2 root n approaching 0. Of course, this tells us that as n approaches 0, we have this whole expression approaching 0 also, right? Of course, the idea of maximization is that you differentiate and then you get something close to 0. So if you differentiate absolute value of x, of course, I think we should get 1 there. And we have 1 all over 1 plus nx squared. No, 1 over 1 plus, no, 1 over 2xn. So if you have 1 over 2xn, so it's like making x the subject of formula now, something. But we are maximizing over x greater than or equal to 0. That's the deal now. That's why the critical point turns out to be x equals 1 over root n. Okay? Because if x is 1 over root n, it means we have something like, so if x is 1 over root n, so it means we have, if you square that, you have 1 over n cancels out. So you have 1 over 1 plus 1 down there. And so it means that's, x at the top is 1 over root n, okay, all over 2. So, and that's why we have this 1 over 2 root n right here. And that approaches 0. Of course, as n approaches infinity, this whole expression approaches 0. So we can say hence convergence is uniform on the real number line. Okay, we have example 3 now. So example 3, we want to see the summation of sine nx over n squared on the real number line. So we see that each term satisfies the absolute value of sine nx over n squared less than or equal to 1 over n squared. Then since convergence of 1 over n, since summation of 1 over n squared converges, the Weierstrass M-test applies. So therefore, we have the summation sine nx over n squared converges uniformly and absolutely on R. Of course, this, if we remove the sine nx part, right? So this expression, of course, we already know that sine x, the absolute value of sine x, the highest it can be is 1, because it will only keep moving between -1 and 1, right? So we know this is always less than or equal to 1 over n squared, because we have something up here. So it is bounded by 1 over n squared, so to speak. And since that the summation of that 1 over n squared converges, then we can say the Weierstrass M-test applies in this situation. Therefore, the summation of sine nx over n squared converges uniformly and absolutely on the real number line. So the consequence is that the sum s of x is continuous, and we may integrate termwise such that integral from 0 to 2 pi of summation from n equals 1 to infinity of sine nx over n squared dx is equal to summation from n equals 1 to infinity of integral 0 to 2 pi sine nx over n squared dx is equal to 0 in that case. Now, let's talk about differentiation failure with uniformity. So differentiation failure with uniformity. Okay, so define fn of x equals 1 over 1 minus cos nx over n on the closed interval 0 to 2 pi. Then we can say that fn prime of x is equal to sine nx. Of course, because if you differentiate 1, it goes. And then here, if you differentiate cos nx, you get n sine nx, and n cancels out. So that simply gives you fn prime of x to be sine nx, like that. So the sequence fn does not converge either, because it doesn't converge, because it diverges. And the lesson here is that differentiation under the limit sign requires uniform convergence of derivatives plus an anchor point, like that. Okay, so we have power series talking about radius and boundary behavior now. So first of all, finding the radius of convergence, I think we already talked about that before. Using the root test from Cauchy-Hadamard, 1 over r is the limits of the supremum as n approaches infinity of the absolute value of Cn raised by 1 over n. And then for ratio test, when limits exist, we have r to be limit as n approaches infinity of absolute value of Cn over Cn plus 1. So that's talking about radius of convergence. And then we have uniform convergence on compact subintervals. So for any 0 less than r less than big R, the series summation Cn into x minus a raised power n converges uniformly on the closed interval a minus r, comma a plus r. And the reason is that if absolute value of x minus a is less than or equal to r, then the absolute value of Cn into x minus a raised power n is less than or equal to absolute value of Cn r raised power n. So since summation of the absolute value of Cn Rn converges for r less than r, then the Weierstrass M-test applies in that situation. So, and we have termwise integration, differentiation and integration. So that's term by term in differentiation and integration. So if s of x is equal to summation of Cn into x minus a raised by n with radius r, then for absolute value of x minus a less than r now, we have the derivative s prime of x equals summation from n equals 1 to infinity, then n Cn into x minus a raised power n minus 1. When you integrate that, we have integral s of x dx equals, of course, this whole thing now, when you integrate it, you get this part, then with the arbitrary constant c. So summation from n equals 0 to infinity. So you can see there's a shifting, there's a movement forward, and then you have summation from n equals 0 to infinity of Cn over n plus 1, all right, into x minus a raised power n plus 1. So as we move it one step further, so we have, n plus 1, Cn plus, so we have n plus 1, taking care of itself up there. So both series have the same radius of convergence, r. So both for derivative and integral. And then we have the boundary behavior. So at x minus a equals r, convergence must be checked point by point on that boundary. Sometimes convergence is sometimes converges absolutely, sometimes it converges conditionally, and sometimes it actually diverges. So there's no universal rule on the boundary. So on the boundary, check every point to be sure of the type of convergence you have. So we have some examples again, talking about geometric series, for instance. Summation. Now, the other time, yeah, we I think we had this geometric, we had x raised power n, right? For geometric series, we have summation from n equals 0 to infinity of x raised power n equals 1 over 1 minus x. And that makes sense, right? Because if you remember sum to infinity, working with series, it ends up being a over 1 minus common ratio, right? So, and that's why, so if you even expand this now, you end up getting things like 1 plus x squared and so on and so forth. So that's why we have this geometric series. So in but given that the absolute value of x is always less than 1, that means that x must always lie between 1 minus 1 and 1. So it must not be minus 1, it must not be 1, but anything in between. So here we can take the radius, you say the radius of convergence is 1, right? So, and it diverges at x equals 1, converges at x equals minus 1. So that's alternating geometric, and the sum is half. Ultimately, the sum to infinity should be half like that. Then we have harmonic type series. So for harmonic type series now, we have something like, so in summation from n equals 1 to infinity of x raised power n over n, and then the radius of convergence is also 1. So at x equals 1, it diverges because it is harmonic series, but at x equals minus 1, it converges conditionally, and it's alternating harmonic, and the sum ends up being minus log ln infinity, natural log of minus ln 2 rather, so minus natural log of 2, right? And then we have exponential series. So for exponential series, you have something like summation from n equals 0 to infinity of x raised power n over n factorial, and the radius of convergence is infinity, right? So it converges uniformly on every bounded interval because the radius is undefined, right? So it will converge uniformly on every bounded interval. So, and it defines the entire function e raised power x, for instance, right? So, and then we have factorial growth series, something like summation from n equals 0 to infinity of n factorial x raised power n. So with this now we can do ratio test where we do an plus 1 over an. So in this case now it means we're going to start with n plus 1 factorial multiplied by x raised power n plus 1 divided by n factorial over x raised power n. And then we can actually break that down. At the end of the day, this is n plus 1 factorial all over n factorial. So you can have n plus 1 times n factorial. So n factorial cancels out. So you have this n plus 1 left. And for this, you have x raised power n plus 1. That's x raised power n times x. That's now divided by x raised power n. So x raised power n cancels out. So at the end of the day, you have absolute value of x. That's why an plus 1 over an is n plus 1 to absolute value of x. And as n increases, of course, this approaches infinity for x not equal to 0 though. So in that case now, the radius of convergence will be 0, because it only converges at x equals 0. Because at x equals 0, the whole thing goes to 0, right? Okay, so let's talk about interchanging limits. Wow, this is quite a lot. Okay, we keep going. So let's talk about interchanging limits, integrals, derivatives. So the clean criteria now. So for limits and continuity, if fn approaches f uniformly and each fn is continuous, then of course f itself is continuous. That function to which the sequence of functions converge is actually continuous itself. We've seen that before. Then we have limits and integrals. Talking about the Riemann version, if fn approaches f uniformly on the closed interval ab and each fn is Riemann integrable, then the limit at n approaches infinity of integral from a to b of fn of x dx is equal to integral from a to b of f of x dx. Then we have limits and derivatives. So if fn, the sequence of functions fn are differentiable on the closed interval ab, then fn of x naught approaches L for some x naught belonging to the closed interval ab, and fn prime approaches g uniformly on the closed interval a comma b. Then fn approaches f uniformly, where f is differentiable and f prime is g. is equal to G. So we have some remarks. So pointwise convergence alone is not enough. So differentiation and integration under the limit sign require uniform convergence because if there's no convergence at some points, there are issues. So pointwise convergence alone is not enough. Differentiation and integration under the limit sign require uniform convergence or even stronger conditions. Then we have the Lebesgue perspective. In the more general setting of Lebesgue integration, one often uses dominated convergence theorem or monotone convergence theorem instead of uniform convergence. Okay, then you have some problem sets. Oh, okay, I think we've gone through some of this, so I'll just flash through them on the screen. So problem set with concise solutions or hints. So for pointwise but not uniform, we already saw fn of x equals x raised to power n, where we saw that fn of x approaches 0 for x belonging to the half closed half open interval because fn of 1 is equal to 1. So, but it is not uniform for xn equals 1 minus 1 over n. It is not uniform because e raised by minus 1 is not 0. Then we now have on the closed interval 0 to 1, you have fn of x equals x raised by n into 1 minus x. So pointwisely, fn of x approaches 0. If you look at this expression, as n increases, you know, this expression as n for fixed value of x, for instance, as n increases, does this really approach 0? Mm, xn is 1 minus x. So pointwise, okay, if you put 0 for x, right? Yeah, okay. Yeah, that makes sense. On this interval, not for all values, on just interval 0 to 1, yeah, that makes sense. So if you put 0, this approaches 0. If you put 1, 1 minus 1 is 0. Good. So on this closed interval, fn of x approaches 0. Correct. So not uniform. So for maximum, the maximum occurs at x equals n over n plus 1 with, so, I mean, to get the maximum, of course, you need to differentiate this and equate to 0. So then we expected to see something like x equals n over n plus 1 with fn into n plus 1 being approximately 1 over 4e. Hence, the supremum of the absolute value of fn of x does not approach 0. So in this case now, we see that it is pointwisely convergent, but uniformly not convergent. So we've seen that for this first two. So the third one also goes the same way. So we have on the real number, every real number thing now, not just close interval 0 to 1. Fn of x is nx over 1 plus n squared x squared. So pointwisely, of course, as n increases, of course, this is going to approach 0. I mean, as x increases, no, n is the focus. For fixed x, as n increases, this approaches 0 for all x. But so it is pointwisely convergent. But it's not uniform because at x equals 1 over n, for instance, okay, so at x equals 1 over n, so fn over 1 over n is equal to 1 over 2. And as far as you can get a value like this, which is not 0, then you say for the norm fn going to infinity, it is equal to half, and that is not equal to 0. As far as you can get a point where that does not go to 0, then you can say that it is not uniformly convergent. Then you can apply the M-test for this set of examples, D. So you can apply the M-test. You want to show that, for instance, that the summation of cos nx over n squared converges uniformly on the real number line. Of course, the boundary is such that cos nx is always less than or equal to 1. We already know it's the maximum is 1, the minimum is minus 1. So it means cos nx lies between minus 1 and 1. That's all this expression is about. And since the summation of 1 over n squared converges, of course, this will definitely converge because as n increases now, 1 over n squared is approaching 0. So you can apply the M-test. Hence, the series converges uniformly. Okay, and then we have this show summation xn over n factorial converges uniformly on any bounded interval that's minus a to a. So the bound here is the absolute value of xn over n factorial is always less than or equal to an over n factorial, right? So since summation of an over n factorial approaches e raised power a, that's the whole exponential thing. So this converges. So M-test applies, right? Hence, convergence is uniform on minus a to a in that case. Then we have term-wise differentiation and integration. So for absolute value, x less than 1, we have summation from n equals 1 to infinity of x raised by n over n equals minus ln 1 minus x. So you can differentiate term-wise and you get d dx of summation from n equals 1 to infinity of x raised by n over n equals summation from n equals 1 to infinity x raised by n minus 1 equals 1 over 1 minus x. So this is valid since convergence is uniform on the closed interval minus r, comma r, for r less than 1. So for x less than 1, we can compute integral from 0 to x, summation from n equals 0 to infinity t raised by n dt. So for termwise integration, now we have integral from n equals 0 to infinity, integral from 0 to x t raised by n dt, and we have this expression, integral from n equals 0 to infinity, x raised by n plus 1 over n plus 1, and that is equal to minus ln 1 minus x, like that, right? That if you do the sum to infinity for this situation. So D, now you have power series talking about radius and boundaries. So find the radius and boundary behavior of summation from n equals 1 to infinity of x minus 2 raised by n by n. The radius is 1 at x equals 3. I mean, you can check my playlist on sequences and series, especially I think, sequences and series, you'll find how to practical ways of getting R now. So at x equals 3 here, you see you have 3 minus 1. 3 minus 2, which is 1. So you have 1 over n, which diverges. Then at x equals 1, you have 1 minus 2. That's minus 1 raised by n all over n, like that. So that's summation from minus 1 raised by n over n, which converges, and it's the alternating harmonic. So here now, you have summation from n equals 0 to infinity of n factorial x raised power n. So the radius r is zero, and it only converges at x equals 0. I think we've seen something like this before. And for this now, summation from n equals 1 to infinity of x plus 1 raised power n over n squared. Radius r is 1 again. At x equals 0, you have summation, when x is 0, you have summation from 1 over n squared, which converges because, this goes to 0. And this also converges for because it's an alternating P series like that. So we have some common pitfalls in all these stories we've been looking at, which I'll just run over. Common pitfalls: assuming pointwise convergence preserves properties. Okay, so uniform convergence is what preserves properties. So assuming pointwise convergence preserves properties is wrong. So pointwise convergence does not preserve continuity, integrability, or differentiability. Uniform convergence or stronger conditions is required. Then next, differentiating limits without checking uniform convergence of derivatives. Before you differentiate, you have to be sure you have to check uniform convergence. So if fn prime approaches G only pointwise, then fn approaches F may fail, or F prime may not even be equal to G. All right. You must have uniform convergence of fn prime and convergence at one anchor point. Like if you forget to check boundary points in power series, that's also another pitfall. So forgetting to check boundary points in power series, if R is the radius of convergence, then at absolute value of x minus a, which is equal to R, behavior must be checked individually. So a series may converge at some points, at some boundary points, and diverge at others. Then trying to prove uniform convergence on an unbounded domain with bounds depending on x. Typically, uniform convergence can only be established on compact subsets. So for entire functions like e raised power x, convergence is uniform only on bounded intervals, right? Then confusing absolute and uniform convergence. Absolute convergence of the summation of fn of x at each x does not imply uniform convergence, for sure. So the M-test is the tool to guarantee both absolute and uniform convergence. Okay, so we have some quick checklists. Finally, we're coming to the end of this. It's been such a long one. So quick checklist, exam style review. So you have uniform convergence test. So for uniform convergence test now, we want to check if the supremum of for x belonging to the set E on the absolute value of fn of x minus f of x approaches 0. So that's what to check for uniform convergence. Then for M-test application, can you bound the function fn of x? Is it possible to have a bound on it, which is less than or equal to mn with summation of mn less than infinity? That's what you want to check for M-test application. For compactness check, On compact set, tools like Dini's theorem or Hayne-Cantor may apply like that. Then you can talk about integrals under limits. So for integrals under limits like that now, so uniform convergence simply means that the limit as n approaches infinity for the integral of f of n is simply the same thing as integral of the limit as n approaches infinity of f of n. So that's integral under limits now. Then what about derivatives under limits? So this needs uniform convergence of fn prime plus convergence of fn of x naught at one point, right? Then you have power series radius. So in this case, it computes r, the radius, which is 1 over the limit of the supremum as n approaches infinity for the absolute value of cn raised to power 1 over n, or for when the limit actually exists. So r is limit as n approaches infinity of absolute value of cn over cn plus 1. Then you have boundary points, okay? So boundary points now always test that the absolute value of x minus a is equal to r separately, and it may converge or diverge. Then you have uniform versus pointwise. So use supremum estimates of moving peaks xn to test non-uniformity. Okay, so you have some mini drills here too. I mean, this is such an elaborate thing. So you want to try your hands. So does fn of x, which is equal to x over n plus x, converge uniformly on the half closed half open interval 0 comma infinity? It is closed above and open above, closed below and open above. So that means 0 is included, but infinity is not. So pointwisely, you see that if you look at this expression as for a fixed value of x, as n approaches infinity, this function goes to 0. So you see fn of x approaches 0 for each fixed x. So that talks about pointwise convergence. But on the other hand, we find the supremum as x for x greater than or equal to 0 for x all over n plus x. This approaches 1 because if you divide it 10 by 10, so x over x, if you have x over x, that's 1. You have n over x plus x over x, which is another 1. So you have 1. So for n over x now, you have 0 here. So at the end of the day, just the whole thing just goes to 1 like that. So it means that as far as you get 1 and it is not 0, so you can say no, it is not uniform on the interval 0 to infinity like that. So but then if you have the closed interval 0 comma a now, so you see that you have supremum for x belonging to 0 comma a, x over n plus x is less than or equal to a over n, and a over n, of course, as n becomes larger, a over n goes to 0. Hence you can talk about hence uniform on compact intervals. So you can see that this is uniformly convergent on this compact interval, but on this other interval, it's not, because you get a kind of limit that is not 0 at some point. Okay. Then what about talking about the radius of the series? Summation x minus 3 raised by n over 2 raised by n. So using the ratio test now, you have the radius to be r equals 2. And then 3, does sine nx over n converge uniformly on r? For fixed x, by Dirichlet's test, series converges pointwise, then but not uniform. Since no uniform control on oscillations, in conclusion, like you can say this converges pointwise, but not uniformly, right? Then you also have uniform limits. So you have uniform limits of continuous functions like that. So if fn approaches f uniformly and each fn is continuous, then f is continuous. That's one of the first things we started with. So this fails with only pointwise convergence. And lastly, the question here is, can we differentiate the summation of x raised by n over n termwise for absolute value of x less than 1? So, and the answer is yes. Inside, you have the absolute value of x less than 1 for uniform convergence on compact now, okay? So differentiated series now becomes something like summation from n equals 1 to infinity of x raised by n minus 1, which is the same thing as 1 over 1 minus x. And that is the end of this very lengthy video on sequences and series, talking about comparing pointwise and uniform convergence like that. So with this, I come to the end of this video. Let me know how helpful this is for you. And if there's something you'd like me to try out, feel very free to let me know. If you have subscribed already, thank you. If you haven't, of course, you don't want to keep missing out on this channel. So please go ahead and subscribe right away and hit the notification bell so you can always get alerted each time a new video is released. And having done that, you can take it a step further by clicking on join to become a member of this channel. And that gives you some special privileges. like maybe having a one-on-one hangout with me and things like that, right? So do that. Ultimately, don't forget to comment, like, and share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing math right. Bye.